Hi students, in this video I am going to talk about the concept of independent random variables, expectation of multivariate distributions and related concepts. Before that, I want to generalize things I discussed in the last video for bivariate random variable to k-dimensional random vector. Okay. In general, the probability distribution of k-dimensional random vector x under bar, which is a vector of k random variables x1, x2, xk, is a function px under bar from script to bk to r, where the script to bk is Borel sigma field in Rk. It is defined like this. B in script to bk assigned to the probability of x under bar belongs to B. Here, this x under bar belongs to B, the event consisting of outcomes omega in this capital omega, for which this k tuple x1 omega, x2 omega, xk omega sitting in P. Okay, this is the event in script f, so this probability makes sense. So this px under bar function will be well defined and it will satisfy three axioms of probability. We can check that. So this px under bar function is valid probability function. This is going to be our probability distribution of k-dimensional random vector. Okay. Similarly, joint CDF of this k-dimensional random vector are going to be fx under bar, which is a function from Rk to R defined like this. Joint CDF value at x1, x2, k is probability of x1 less than or equal to x1, x2 less than or equal to x2, xk less than or equal to xk. In terms of probability distribution, we can say this one as px under bar of this basic event minus infinity to x1 cross minus infinity to x2 cross so on minus infinity to xk. Okay, so the probability of this basic event under this px under bar going to be the joint CDF value at x1, x2, xk. Okay, now properties of joint CDF. Joint CDF function is non-decreasing right continuous with respect to each coordinate xi for I equal to 1 to k. That means if you fix every coordinate except xi, then joint CDF is going to be function of single variable xi. As a function of single variable xi, it is a non-decreasing right continuous function. That's what it means. And this limit of joint CDF is 1 as you let xi go to infinity for all I equal to 1 to k, and the limit of joint CDF is 0 if you let any xi go to minus infinity. Okay, these are the properties of joint CDF and these properties completely characterize joint CDF of random vector. Okay, fine. Now for discrete random vector x under bar, the points x1, x2, xk in Rk for which the probability of x1 equal to x1, x2 equal to x2, so on, xk equal to xk positive will be support. Okay, and the joint PMF is going to be function from Rk to R defined like this. Joint PMF value at x1, x2, xk going to be the probability of x1 equal to x1, x2 equal to x2, so on, xk equal to xk if this x1, x2, xk coming from support of x under bar, otherwise 0. Okay, this is a joint PMF of k-dimensional random vector. And the properties, first of all, it should be a non-negative function and sum of the joint PMF values over the support must be equal to 1. These are the two properties of joint PMF which will completely characterize joint PMF. That means if there is any function from Rk to R satisfying these two properties, then it will be a joint PMF of some k-dimensional random vector. Okay. Next, for any Borel set in script to bk, the probability of x under bar belongs to B can be obtained simply summing up the joint PMF values over this B intersection with Sx under bar. Okay, fine. Okay, for a random vector x under bar, which is a k-dimensional random vector x1, x2, xk. Here xi1, xi2, xi are some subcollection of the random variables from x1, x2, xk. If you want joint PMF of this subcollection of random variable xi1, xi2, xir, okay, what we do is simply sum of the joint PMF of this x under bar over the support of the remaining variables. Okay, it is just generalization of what we did in the bivariate case. If you have a bivariate random variable xy, if you want to get the PMF of x, what you did, you sum up joint PMF values over the support of remaining variable. Okay, here also to get the joint PMF of xi1, xi2, xir, we are summing up the joint PMF values over the support of the remaining variables. Okay, fine. Next conditional PMF of is xir plus 1, xir plus 2, xin, given that xi1 equal to small xi1, xi2 equal to small xi2, so on, xir equal to small xir, defined like this. Okay, it is again generalization of what we did in the bivariate case. The conditional PMF of x given y. How did we define this? The joint PMF value at ij by the PMF of y at j. Here also same thing. Joint PMF of x1, x2, xk at x1, x2, xk by the PMF of what is given here. Okay, xi1, xi2, xir at xi1, xi2, xir. Okay, it is just generalization of what we did in the bivariate case. Okay, fine. Now, joint PDF of continuous random vector x under bar is a non-negative function small f x under bar which is connected to joint CDF of x under bar like this. This is how you can get joint CDF of x under bar from this joint PDF. Okay, integrating like this. Further, if you happen to know your joint PDF is a continuous function, then you can also get joint PDF from joint CDF like this. Differentiating joint CDF k times once with respect to each coordinate. This is all. If you differentiate joint CDF k times once with respect to each coordinate, then you will end up with joint PDF of random vector x under bar. Okay, fine. Next, properties of joint PDF. Joint PDF must be non-negative function and total integral must be equal to 1. These are the two properties of joint PDF which will completely characterize joint PDF. That means any function from Rk to R which satisfying these two properties will be joint PDF of some k-dimensional random vector. Okay. Now for any Borel set B in script Bk, the probability of x under bar B can be obtained integrating joint PDF over B. Okay. Here this integral is k-dimensional multiple integral. Okay. Next. Okay, here we have a k-dimensional random vector x under bar which is a vector of k random variables x1, x2, xk, and here xi1, xi2, xi are some subcollection of the random variables from x1, x2, xk. If you are interested in getting joint PDF of this random vector, what you can do is you can integrate the joint PDF of x under bar with respect to remaining variables xir plus 1, xir plus 2, xik, which is just generalization of what we know in the bivariate case. In the bivariate case, to get the PDF of x, what we did, we integrated joint PDF with respect to remaining variable. Here also we are doing the same thing. To get the joint PDF of xi1, xi2, xir, we are integrating joint PDF of x under bar with respect to remaining variables that are xir plus 1, xir plus 2, xik. Okay. Similarly, we can talk about conditional PDF of xir plus 1, xir plus 2, xik, given that xi1, xi2, xir. Okay, this is defined like this. Okay, which is generalization of what we know in the bivariate case, that is conditional PDF of x given y. How did we define this? Joint PDF at xy by PDF of y at y. Okay. Here also same thing. Joint PDF of x under bar by the PDF of what is given xi1, xi2, xir. Okay. These are the generalization from bivariate case to k-dimensional random vector. Okay. Fine. Independent random variables. Okay. We already know the meaning of two events being independent, right? What is the definition? Two events A and B are in event space script F are said to be independent if the probability of A intersection B equal to probability of A times probability of B. This is the definition for saying that two events A and B are independent. Okay. Now let me define independence of two random variables. Here is the definition. X and Y are two random variables that are defined on same probability space omega script of P. We say x and y are independent if probability of xy belongs to b1 cross b2 equal to probability of x belongs to b1 times probability of y belongs to b2 for all b1 b2 belongs to script b, which is the Borel sigma field in R. Okay, if b1 b2 are two Borel sets in R, then b1 cross b2 going to be Borel set in R2. Okay, so if you want to put this definition in terms of joint probability distribution and marginal probability distribution, the left hand side I can write the pxy value at b1 cross b2. Right hand side I can write px of b1 times py of b2 for all b1 b2 belongs to script b. That means joint probability distribution of xy should be product of the marginal probability distributions. Okay. Okay. Now let us try to see the meaning of the definition. So the left hand side xy belongs to b1 cross b2 means x belongs to b1, y belongs to b2. Let me write like this. Left hand side probability of x belongs to b1 and y belongs to b2. Right hand side as it is, probability of x belongs to b1, probability of y belongs to b2. Okay. Now let us say A is the event, that is x belongs to b1. That means it is an event consisting of outcomes in sample space for which x omega sitting in b1, which is going to be event in script F. Let us say B is the event that y belongs to b2. That means this is the event consisting of outcomes in sample space for which y omega sitting in b2. This is also event in script F. Now let me write down this in terms of A and B. The left hand side is going to be probability of A, comma means end means intersection. Probability of A intersection B, right hand side is going to be probability of A times probability of B. That means A and B are independent. Okay, what this definition says intuitively, events that are described by X should be independent of events that are described by Y. That's when we say X and Y are independent. Okay. If this definition holds, we can guarantee that events that are described by X are independent of events that are described by Y. Okay. So this is the meaning of given definition, that is joint probability distribution is product of the marginal probability distribution. Okay. Usually we don't work with the probability distribution functions Rather, we work with CDFs, PMFs or PDFs, right? Let me give alternative definitions of independence of two random variables. Okay. Equivalently, we can say X and Y are independent if joint CDF equal to product of marginal CDFs. Okay. Further, if you are working with a discrete bivariate random variable, then you may have access to joint PMF. In that case, you can use this definition. That is, check if joint PMF is product of marginal PMF. Okay. Or if you are working with a continuous bivariate random variable, then you may have access to joint PDF. In that case, you can use this definition. That is, check if joint PDF is product of marginal PDFs. Okay. So these are the definitions that can be used to check if X and Y are independent. Okay. Fine. Okay. Now let me generalize definition for K random variables. We say K random variables x1, x2, xk defined on same probability space omega script of p are said to be independent if joint CDF equal to product of marginal CDFs. This is a general definition. Okay. Further, if x1, x2, xk are discrete type and if you have access to their joint PMF, then you can use this definition for independence of x1, x2, xk. That is, to see if x1, x2, xk are independent, we have to check if joint PMF is product of marginal PMFs. Okay. If x1, x2, xk are continuous type and if you have access to their joint PDF, then you can use this definition for independence of x1, x2, xk. That is, to see if x1, x2, xk are independent, we have to check if joint PDF equal to product of marginal PDFs. Okay. This is how we can check if x1, x2, xk are independent. Okay. Fine. Okay, here x and y are two random variables with a joint PDF f of x y equal to y into e power minus of x plus y for x positive, y positive, 0 otherwise. Okay, let's check if x and y are independent. For that, we need to check if joint PDF equal to product of marginal PDFs. Okay. First, let us get hold of PDF of x and PDF of y. How do you get the PDF of x? We have to integrate joint PDF with respect to y. Okay, y limits are going to be 0 to infinity. So we are integrating joint PDF y into e power minus of x plus y with respect to y from 0 to infinity. Here, first of all, if you write e power minus x out, okay, this is going to be y e power minus y dy. This y you can realize as y to the power of 2 minus 1, so that this integral can be seen as gamma integral. So it's going to be gamma 2. So e power minus x gamma 2 value 1 factorial. So the PDF of x is e power minus x for x positive, 0 for x less than or equal to 0. This is the PDF of x. Now let us find out the PDF of y. How do you get the PDF of y? Integrating joint PDF with respect to x. Okay. Here x limit is going to be 0 to infinity. So we are integrating joint PDF y into e power minus of x plus y with respect to x from 0 to infinity. Here we can write y e power minus y outside. Then it's going to be integral 0 to infinity e power minus x dx. Here we can realize something x to the power of 1 minus 1, so that this integral can be seen as gamma 1. So y times e power minus y gamma 1. The gamma 1 value 0 factorial. So the PDF of y is going to be y into e power minus y for y positive, 0 for y less than or equal to 0. Okay, so we got the PDF of x and PDF of y. Now it's pretty clear that the joint PDF in fact equal to product of marginal PDFs. So therefore x and y are independent. Okay, fine. Okay, next. In the last video, we worked with this joint PDF These are the marginal PDF that we got. Here we can clearly see that joint PDF not equal to product of marginal PDFs. Therefore, we can say X and Y are not independent. Okay, fine. Next, here X and Y are discrete type random variables with this following giant PMF table. Okay, from this giant PMF, we can actually find out marginal PMF by summing up rows. You can get the PMF of X. By summing up column, you can get the PMF of Y. So, by summing up the first row 1 by 4 plus 1 by 4, we get a 1 by 2, which is Px of 0. By summing up the second row, again 1 by 4 plus 1 by 4, that is 1 by 2, that is the Px of 1. Similarly, by summing up the columns, we get Py of 0 as a 1 by 2, Py of 1 also 1 by 2. Now we can clearly see that joint PMF actually equal to product of marginal PMFs. Therefore, X and Y are independent. Okay? Fine. When X and Y are independent, conditional distributions will be same as marginal distributions. That is, if X and Y are independent discrete random variables, then conditional PMF of X given Y will be same as marginal PMF of X. Conditional PMF of Y given X will be same as marginal PMF of Y. Let me show you one here. Conditional PMF of X given Y at I given J, by definition is what? Joint PMF value at Ij by PMF of Y at J. When X and Y are independent, joint PMF we can write product of marginal PMF. So the numerator we can write Px of Y times Py of J by Py of J. These two get cancelled, you end up with Px of Y. Okay, we showed this. Similarly, you can show this. Okay. In the same way, if X and Y are independent continuous random variables, then conditional PDF of X given Y will be same as marginal PDF of X. Similarly, conditional PDF of Y given X will be same as marginal PDF of Y. Okay, fine. Now let me define expectation of function of bivariate random variable. Let G be the function from R square to R, which is a function of two real variables. If xy is the discrete bivariate random variable with a joint PMF small pxy, then expectation of g of xy defined to be this weighted sum of g of ij values with the weights being corresponding joint PMF values at ij. Here the summation is double summation. First summation runs over I, second sum runs over j, where this ij come from support of xy. Okay. Of course, provided this right hand side sum converges absolutely. That means if this sum is finite, then we say expectation of g of xy exists and expectation of g of xy defined to be this summation. Okay, fine. Next, if xy is a continuous bivariate random variable with joint PDF small fxy, then expectation of g of xy defined to be this double integral, provided this double integral converges absolutely. That means if this integral is finite, then we say expectation of g of xy exists and this integral defined to be expectation of g of xy. Okay. Now let us talk about expectation of function of k-dimensional random vector. In general, if x under bar, which is a vector of k random variables x1, x2, xk, is a discrete k-dimensional random vector with a joint PMF small px under bar, then expectation of g of x1, x2, xk defined to be this summation provided this right hand side sum converges absolutely. Similarly, if x under bar is the continuous k-dimensional random vector with a giant PDF small f x under bar, then expectation of g of x1, x2, xk defined to be this multiple integral provided this right hand side integral converges absolutely. Okay, these are the definitions. Fine. Next theorem. If expectation of g1 xy, expectation of g2 xy exist, then expectation of k1 g1 xy plus k2 g2 xy exist for all k1 k2 in R. Not only that, then expectation of this k1 g1 xy plus k2 g2 xy simply going to be k1 times expectation g1 xy plus k2 times expectation of g2 xy. Okay, that is, if expectation g1 xy, expectation g2 xy exist, then expectation of every linear combination of g1 xy, g2 xy exist. Not only that, expectation of that linear combination of g1 xy, g2 xy going to be linear combination of expectation of g1 xy, expectation of g2 xy. Okay, fine. Let's prove this theorem. Let me prove this theorem for continuous bivariate case. Similarly, we can prove for discrete bivariate case. Okay. What is given here? Expectation of g1 xy, expectation of g2 xy exist. That means we know these two absolute integrals are finite. Okay. So now we have to show expectation of k1 g1 xy plus k2 g2 xy exist. For that, we need to show this integral is finite. Okay. So let me consider this integral and show this is finite. Okay. Okay. Now I can say this integral less than or equal to this one, because here this part of integrand mod k1 g1 xy plus k2 g2 xy, I can write less than or equal to mod k1 mod g1 xy plus mod k2 mod g2 xy, because of triangle inequality. So I can say this integrand will be less than or equal to this integrand. So this integral will be less than or equal to this integral. Okay, fine. Now by using linear property of integral, we can write this integral equal to this one. Okay, this is the linear property of integral. Now we know this is finite, this is finite. So this whole thing is going to be finite. Okay, so we can say expectation of k1 g1 xy plus k2 g2 xy exist. Okay, fine. Now let us show expectation of k1 g1 xy plus k2 g2 xy equal to k1 expectation g1 xy plus k2 expectation g2 xy. Okay. Now, by definition, if expectation of k1 g1 xy plus k2 g2 xy exists, then it is going to be this. Okay, because simply think like this is g of xy, so we are simply writing here g of xy. Okay, okay. Now this right hand side, using linear property of integral, we can write k1 times this double integral plus k2 times this double integral, and this is exactly expectation of g1 xy, and this is exactly expectation of g2 xy. So we can write the right hand side k1 expectation of g1 xy plus k2 expectation of g2 xy. So therefore we have this linear property. Okay, if expectation g1 xy, expectation g2 xy exist, then expectation of every linear combination of g1 xy, g2 xy exist. Not only that, expectation of this linear combination of g1 xy, g2 xy going to be linear combination of expectation g1 xy comma expectation g2 xy. Okay, fine. Next corollary. Corollary 1. Instead of just two functions g1 of xy, g2 of xy, you may have n functions g1 of xy, g2 of xy, so on, gn of xy. If you happen to know expectation of each of this g1 of xy, g2 of xy, so on, gn of xy exist, Then you can say expectation of every linear combination of this g1 of xy, g2 of xy, so on, gn of xy exists. Not only that, expectation of this linear combination of g1 xy, g2 xy, gn xy going to be linear combination of expectation of g1 xy, expectation of g2 xy, so on, expectation of gn xy. This is a general result. We can easily prove it using induction. The base case going to be n equal to 2 that we proved in above theorem. Okay. Corollary 2. Let xy be the bivariate random variable with both expectation x, expectation y exist. Then expectation ax plus by exist for all ab. Not only that, expectation of ax plus by going to be a times expectation x plus b times expectation y. It follows from above theorem. Simply take k1 equal to a, k2 equal to b, g1 of xy to be x, and g2 of xy to be y. Then this corollary 2 follow from above theorem. Okay, fine. Next, corollary 3. If x under bar, which is a vector of k random variables x1, x2, xk, that is a k dimensional random vector. If here g1, g2, gn are n functions from rk to r, like gi is a function from rk to r, which is a function of k real variables. If expectation of gi of x under bar exists for I equal to 1 to n, then expectation of any linear combination of this g1 x under bar, g2 x under bar, so on, gn x under bar exists. Not only that, expectation of this linear combination of g1 x under bar, g2 x under bar, so on, gn x under bar going to be linear combination of expectation of g1 x under bar, expectation of g2 x under bar, so on, expectation of gn x under bar. Okay, so this is the general result. Okay, next, corollary 4. Let x under bar is the k dimensional random vector, which is a vector of k random variables x1, x2, xk, with each expectation xi exists for I equal to 1 to k. Then expectation of summation I equal to 1 to k ai xi exists for all a1, a2, ak. Not only that, expectation of the summation I equal to 1 to k ai xi going to be summation I equal to 1 to k ai expectation of xi, which simply follow from corollary 3. Just take n equal to k and gi of x under bar equal to xi and ki equal to ai for I equal to 1 to so on k. Then this corollary 4 follow from corollary 3. Okay, fine. Next, theorem. If x comma y are independent random variables, then for any functions g comma h from R to R, expectation of g of x time h of y equal to expectation of g of x time expectation of h of y. Of course, this is true when all expectations in the expression exist. Okay. Let me prove it in the continuous bivariate case. Similarly, you can prove it for discrete bivariate case. Okay. Here, first of all, x and y are independent. That means joint PDF equal to product of marginal PDFs. Okay. Now let me start with the left hand side. Expectation of g of x time h of y is what? By definition, double integral of g of x h of y f of x y dx dy. Now we can replace this joint PDF with product of marginal PDFs. Okay. Then this integrand we can write product of two functions. One is function of x alone, other is function of y alone. Like this, I can write g of x time f of x time h of y times f of y. Okay. Now this double integral we can write product of two integrals like this. Okay. This is the one integral, this is another integral. This is nothing but expectation of g of x. This is nothing but expectation of h of y. So therefore, the right hand side is what? Expectation of g of x time expectation of h of y. Therefore, we have expectation of g of x time h of y equal to expectation of g of x time expectation of h of y when x and y are independent. Okay, fine. Corollary, if x and y are independent, then we have expectation of xy equal to expectation of x time expectation of y. It simply follows from above theorem by taking g of x equal to x, h of y equal to y. Okay, fine. Next, Cauchy's quartz inequality. Here is the statement. Let xy be a bivariate random variable, then expectation of xy whole square always less than or equal to expectation x square times expectation y square. Of course, when all expectations in this inequality exist. Okay, let's prove this. For t belongs to R, consider this expectation of tx plus y whole square. This is going to be positive unless y equal to minus tx with probability 1. In that case, this inequality holds with equality. We can see that. When y equal to minus tx with probability 1, this tx plus y will be degenerate random variable at 0. So this expectation of tx plus y whole square is going to be 0. Okay, fine. Now let's focus on this expectation. This is positive unless this is the case. Okay, so if I expand inside this tx plus y whole square, I can write like this. Okay, expansion of tx plus y whole square is what? T square x square plus 2txy plus y square. Okay, this expectation of t square x square plus 2txy plus y square is positive. Now if we apply linear property of expectation, we can take expectation inside like this. So we can write t square expectation x square plus 2t expectation xy plus expectation y square. This is positive. Okay, let me call it 1. So this 1 is quadratic inequation in t. Okay, this look like actually at square plus bt plus c positive. Okay, here a equal to expectation x square, b equal to 2 times expectation xy, and c equal to expectation y square. And this inequality true for all t belongs to R unless this is the case, right? That happen only when this discriminant, that is b square minus 4ac negative. So what is the b square minus 4ac? Here the discriminant delta b means 2 times expectation xy, 2 times expectation xy whole square minus 4ac, 4 times expectation x square times expectation y square is negative. Okay, this we should know from knowledge of quadratic expression from PUC, because here anyway a is positive, right? So the parabola will be completely like this, above. Okay, so that means the parabola is not crossing x-axis, means we don't have a real roots. That means we have imaginary roots. Okay, that's why this discriminant must be negative. Okay, fine. Now, so we have 4 times expectation xy whole square minus 4 times expectation x square times expectation y square less than 0, which is equivalent to expectation xy whole square less than expectation x square times expectation y square. Okay, we always have this strict inequality unless y equal to minus tx with probability 1 for some t. Okay, if y equal to minus tx with probability 1 for some t, we have equality. So in general, we have following inequality, that is expectation xy whole square less than or equal to expectation x square times expectation y square. Okay, this is something called Cauchy's quartz inequality. I am going to use it in future results. One point I want to emphasize here, equality holds only when y equal to minus tx with probability 1 for some t. Okay, otherwise we have a strict inequality. Okay, fine. Now let me define what are called product moments of bivariate distributions. Okay, here the non-central product moment of order r comma s denoted by mu dash rs defined to be expectation of x to the power of r y to the power of s, provided this expectation exists. Okay, as special cases we can see that mu dash 1 comma 1 is expectation xy. Here we are taking r equal to 1, s equal to 1, and mu dash 1 0 going to be expectation of x. Here we are taking r equal to 1, s equal to 0. So we have expectation x. Sometimes we can also denote by mu x, and mu dash 0 comma 1 going to be expectation y. Here we are taking r equal to 0, s equal to 1. So we have expectation y. Sometimes we also denote by mu y. Okay. Similarly, the central product moment of order r comma s denoted by mu r comma s defined to be expectation of x minus mu x all to the power of r times y minus mu y all to the power of s, provided this expectation exists. As a special case, we can see that mu 1 comma 1 is expectation of x minus mu x times y minus mu y. This is going to be important quantity for us. Next we are going to define this one as something called covariance of x and y. Definition: the covariance between x and y denoted by this, we read it as covariance of x and y defined to be expectation of x minus expectation of x times y minus expectation of y. This is the definition. Okay. This covariance of x and y measures the average of product of deviations of x and y from their means. Fine. Note, the covariance of xy going to be expectation of xy minus expectation of x times expectation of y. So usually we use this tool to compute covariance of x and y. Though this is a definition, but to compute covariance of xy, we are going to use this one. Expectation of xy minus expectation of x times expectation of y. Okay, fine. Let me show you what is the covariance of x and y. By definition, the right hand side is expectation of x minus expectation x times y minus expectation y. So if I multiply inside expectation, what I get? Xy minus x times expectation y minus expectation x times y minus plus expectation x times expectation y. Here expectation y is a number, expectation x is a number, this is a number. By applying linear property of expectation, I can write expectation xy minus expectation x times expectation y minus expectation x times expectation y. Expectation of a constant will be constant expectation of x times expectation of y. Now these two cancel. Now what you have? Expectation xy minus expectation x times expectation of y. This is the covariance of x and y. Okay. To compute covariance of x and y, we use this formula. Okay. Okay. And this covariance of xy also denoted by this sigma xy. Okay. Sometimes this covariance of xy also denoted by this sigma xy. Note 2, if x and y are independent, then covariance of xy will be 0. Because we have just seen that covariance of xy is what? From note 1, expectation xy minus expectation x times expectation y. But we know that when x and y are independent, expectation xy will be same as expectation x times expectation y. Okay, that's why whenever we have x and y are independent, then the covariance of xy is going to be 0. But what about converse? If covariance of x y 0, can we say x and y are independent? No. Here is an example. Converse is not true. If I take x is a standard normal random variable and y equal to x square, obviously you can see that y is not independent of x, y equal to x square, y depend on x, right? Here x and y are not independent. Here x and y are not independent. But we are going to see that covariance of xy is going to be 0. Okay. First of all, we know that for standard normal random variable, all odd order moments are 0. That is expectation x0, expectation x cube 0, expectation x to the power of 5 0, like that. So expectation x is 0 and expectation x square is going to be variance of x plus expectation of x whole square, that is going to be 1. Okay. Now the covariance of xy, that is what? Expectation xy minus expectation x time expectation y. Left hand side we have expectation of x into x square. Right hand side expectation x time expectation x square. Now, so we have expectation x cube minus expectation x time expectation x square, but expectation x cube will be 0 because the odd order moment of standard normal random variable, and expectation x is 0, so the whole thing is 0. Okay, so here covariance of x by 0, but x and y are not independent. So whenever x and y are independent, we have a covariance of x by 0, but converse may not be true. This is the counter example. Okay. Theorem: let x, y be bivariate random variable. Then we have following results. Covariance of x comma y same as covariance of y comma x. Covariance of x comma x same as variance of x. Covariance of x plus a comma y plus b same as covariance of x comma y, and covariance of x comma by same as ab times covariance of x comma y. Okay, these results directly follow from definition of covariance of x comma y. What is the covariance of x comma y definition? The expectation of x minus expectation x times y minus expectation y. Okay, fine. As you can see, the definition is symmetric in x and y. Obviously, we should have this covariance of x comma y same as covariance of y comma x. If you take y equal to x, the right hand side become expectation of x minus expectation x whole square. So that should be variance of x. So this is also clear. Similarly, you can verify 3 and 4. Okay. So feel free to verify. These are easy. Just directly follow from definition. Okay. Fine. Here, result 3 says that if you shift x by a and y by b, covariance will not be affected. Result 4 says that if you scale x by a and y by b, then covariance will be scaled by ab. Okay, fine. Theorem: let x1, x2, so on, xn and y1, y2, so on, ym are random variables depend on probability space omega script of p, then covariance of summation I equal to 1 to n xi comma summation j equal to 1 to m yj equal to this double summation of covariance of xi comma yj, where this first summation runs over first index I from 1 to n, second summation runs over second index j from 1 to n. This is the result. Okay, let's prove this. Fine. Here, let us start with the left hand side. Let's think like this is x, this is y. Apply the definition of covariance of xy. What is the definition of covariance of x comma y? Which is the expectation of x minus expectation x times y minus expectation y. Okay. Now Let's start with the left hand side and apply the definition of covariance of x comma y, where x is this, y is this. So we have this expectation of the summation I equal to 1 to n xi minus expectation of summation I equal to 1 to n xi times summation j equal to 1 to m yj minus expectation of summation j equal to 1 to m yj. Okay, fine. Here if I apply the linear property of expectation, then I can write summation I equal to 1 to n expectation xi. Similarly here also if I apply linear property of expectation, then I can write summation j equal to 1 to m expectation yj. Okay, in the next step we have this. Okay, after applying linear property here, again this part we can write summation I equal to 1 to n xi minus expectation xi, and this summation I can write summation j equal to 1 to m yj minus expectation yj. Okay, so that's the next thing we are writing. Now if I multiply these two summations inside, so I will end up with a double summation I equal to 1 to n j equal to 1 to m xi minus expectation xi times yj minus expectation yj. Okay, that's what we have. In the next, now by applying linear property of expectation, we can take this expectation inside and we can write like this, and this is exactly covariance of xi comma yj. So therefore we have this result. Covariance of summation I equal to 1 to n xi comma summation j equal to 1 to m yj going to be this double summation of covariance xi comma yj, where this first sum runs over first index I from 1 to n, second summation runs over second index j from 1 to m. Okay, so this is the result we have. Okay, next corollary. So covariance of summation I equal to 1 to n aixi comma summation j equal to 1 to m bj yj going to be double summation of ai bj covariance of xi yj. Here the first summation runs over first index I from 1 to n, second summation runs over second index j from 1 to n. Okay, this directly follow from above theorem. From above theorem, I can write this step summation I equal to 1 to n, summation j equal to 1 to m, covariance of ai xi comma bj yj. Okay, in the next step, this covariance of ai xi bj yj we can replace with ai bj covariance of xi comma yj. Okay, that's why we have this result. Fine. Okay, next theorem. Let x1, x2, so on xn are n random variables defined on probability space omega script of p. Then variance of summation I equal to 1 to n ai going to be summation I equal to 1 to n ai square variance of xi plus 2 times double summation of ai aj covariance of xi comma xj, where this first summation runs over first index I from 1 to n, second summation runs over second index j from 1 to n, where I less than j. Okay, as we can see, we don't have a linear property for variance. In the case of expectation, we have seen that expectation of linear combination of random variables is going to be linear combination of expectation. That is, we have seen that expectation of linear combination of xi is equal to linear combination of expectation of xi, right? That's not true with a variance. This is how we deal with variance of linear combination of xi. Okay, fine. Let's prove this. First of all, we know something. The variance of a random variable x we can write in terms of covariance like this. Covariance of x comma x equal to variance of x. If you think this is like x, okay, now variance of x we can write covariance of x comma x, okay, fine. Now using above theorem, this covariance we can write this double summation aij covariance of xi xj. Here the first summation runs over first index I from 1 to n. Second summation runs over second index j from 1 to n. I am writing this from above theorem. Okay. Now let me separate I equal to j terms in this double summation like this. Okay. These are the I equal to j terms. Summation I equal to 1 to n ai square covariance of xi comma xi. These are the I not equal to j terms. Double summation aiaj covariance of xi xj. Here first summation runs over first index I from 1 to n, second summation runs over second index j from 1 to n, but here I not equal j. This is how I am separating total terms into I equal to j terms, I not equal j terms. Okay. Here the covariance of xi comma xi going to be variance of xi. Fine. In this double summation, ijth term will be same as jth term. For example, term corresponding to I equal to 1, j equal to 3 will be this one, right? A1, A3 covariance of x1 comma x3. The term corresponding to I equal to 3, j equal to 1 will be what? A3, A1 covariance of x3 comma x1. But these two are same. Likewise, every term will be repeated twice. Now, this summation we can write summation I equal to 1 to n ai square variance of xi, and this summation we can write 2 times double summation aiaj covariance of xi xj. If the first summation runs over first index I from 1 to n, second summation runs over second index j from 1 to n, but this time we are keeping I less than j because we are not writing both these terms, we are keeping only this term, discarding this, but we are multiplying by 2. Okay, that should do. Fine. So this is going to be formula for variance of linear combination summation I equal to 1 to n aixi. This is how we deal with the variance of linear combination of xi. Okay, fine. Corollary 1, variance of x plus or minus y going to be variance of x plus variance of y plus or minus 2 times covariance of xy. These things follow from above theorem. Variance of x plus y will be easy. Let me show you variance of x minus y. First of all, this x minus y we have to realize like 1 time x plus minus 1 time y. Okay. Now using above theorem we can write 1 square times variance of x plus minus 1 square times variance of y plus 2 times 1 time minus 1 covariance of xy. So therefore you can write variance of x plus variance of y minus 2 covariance of xy. Okay, fine. Next, corollary 2, if x1, x2, so on, xn are independent random variables, then we should have covariance of xi xj 0 for I not equal to j. In that case, the variance of summation I equal to 1 to n ai xi going to be simply this. Summation I equal to 1 to n ai square variance of xi, because all these covariant terms will be vanished, right? So this is going to be much simpler formula when we have n independent random variables. Okay, so we don't have to deal with any covariance term because all will be 0. Fine. Next, if x and y are independent random variables, then variance of x plus or minus y going to be same as variance of x plus variance of y, because this covariance of xy will be 0 when x and y are independent. So we have this, whether variance of x plus y or variance of x minus y, both will be equal to variance of x plus variance of y. Okay. Okay. Let us say we have a bivariate random variable xy. From its distribution, let us say we got a random sample of size n like this: x1, y1, x2, y2, so on. We got a n data point from its distribution. Let's say we plot scatter diagram. Okay. If it's scatter diagram like in figure 1, then we can say that there is a strong linear relationship between x and y in positive direction. When I say positive direction, I mean with a positive slope. That means when x increases, y also increases. Okay. As we can see, there is a strong linear trend in positive direction. So we can say there is a strong linear relationship between x and y. If it is like in figure 2, still we see there is a linear trend in positive direction, but not so strong. So we can say there is a moderate linear relationship between x and y in positive direction. If it is like in figure 3, we can see that there is no linear trend at all. So we can say there is no linear relationship between x and y. If it is like in figure 4, as we can see, these data points are perfectly concentrated along the line. So we can say there is a perfect linear relationship between x and y in positive direction. Okay. If it is like in figure 5, still we see some linear trend, but it's kind of weak one. So we can say there is a weak linear relationship between x and y in positive direction. Okay. Similarly, if it is like in figure 6, so we can say there is a strong linear relationship between x and y, but in negative direction. When I say negative direction, I mean with a negative slope. That means when x increases, y decreases. Okay. Similarly, if it is like in figure 7, we can say there is a moderate linear relationship between x and y in negative direction. If it is like in figure 8, as we can see, there is no linear trend, so we can say there is no linear relationship between x and y. If it is like in figure 9, then we can say there is a perfect linear relationship between x and y in negative direction. If it is like in figure 10, we can say there is a weak linear relationship between x and y in negative direction. Okay, fine. Now we want a tool to measure this degree of linear relationship between x and y. Okay. Next we are going to define something called correlation coefficient, which measure this degree of linear relationship between x and y. Okay. Next, correlation coefficient. The correlation coefficient between two random variables x and y denoted by rho xy and defined as covariance of xy by standard deviation of x times standard deviation of y. Okay, so this is a quantity which measures degree of linear relationship between x and y. First, I am going to show that this correlation coefficient always between -1 and 1. Okay. Theorem: for any two random variables x and y defined on probability space omega script of p, the correlation coefficient between x and y always between -1 and 1. Okay, the rho xy always between -1 to 1. Okay, we have to prove this. We are going to prove it using Cauchy-Squarge inequality. What is Cauchy-Squarge inequality? Expectation xy whole square less than or equal to expectation x square times expectation y square. Okay, and we also know that here this equality occur only when y equal to minus tx with probability 1 for some t belongs to R. Okay, this is what we know from Cauchy-Squarge inequality. So I'm going to apply Cauchy's coordinate inequality for these random variables x minus mu x, y minus mu y. Okay. So by Cauchy's coordinate inequality, we have this expectation of x minus mu x, y minus mu y whole square less than or equal to expectation of x minus mu x whole square times expectation of y minus mu y whole square. By definition, this is nothing but variance of x, this is nothing but variance of y, and this is nothing but correlation coefficient between x and y. Okay, so we have this sigma xy whole square less than or equal to sigma x square sigma y square. Next step, I can write this sigma xy by sigma x sigma y whole square less than or equal to 1. So I can get rid of the square. I can write mod sigma xy by sigma x sigma y less than or equal to 1. That implies I can say minus 1 less than or equal to sigma xy by sigma x sigma y less than or equal to 1. So therefore, we have a correlation coefficient between minus 1 and 1. Okay, so we have a correlation coefficient always between minus 1 and 1. Okay, fine. And here rho xy take the value 1 or minus 1 only when equality occur in Cauchy's coordinate inequality. And we know equality occur in Cauchy's coordinate inequality when y minus mu y equal to minus t times x minus mu x with probability 1. Okay, for some t. Okay, that's when we have a equality in Cauchy's coordinate inequality. That's when the rho xy will be either 1 or minus 1. Let us analyze these two cases. Okay, case 1, rho xy equal to 1. That means expectation of x minus mu x times y minus mu y by sigma x sigma y equal to 1. In the above slide, I mentioned that this rho xy takes extreme values minus 1 or 1 only when this y minus mu y equal to minus t of x minus mu x with probability 1 for some t belongs to R, right? Let's figure out what is this t. Okay, so what I'm going to do, I'm going to substitute y minus mu y equal to minus t of x minus mu x here. Okay, so we have this. So if I take minus t out in the numerator, I will have minus t of expectation x minus mu x whole square. So I can write minus t of sigma x square by sigma x sigma y. The sigma x, the square will be gone. So the t value will be minus sigma y by sigma x. Okay, fine. Now, so in this case, we have y minus mu y equal to, here minus minus plus, y minus mu y equal to sigma y by sigma x of x minus mu x with probability 1. Okay, so I can also write, if I take minus mu y this side, probability of y equal to sigma y by sigma x times x plus mu y minus sigma y by sigma x times mu x equal to 1. Okay, so I can write y equal to ax plus b with probability 1, where a is sigma y by sigma x, which is a positive, and b is mu y minus sigma y by sigma x times mu x. That means we can say that when correlation coefficient is 1, y is perfectly linearly related with x in positive direction. Okay, fine. Similarly, in case 2, when rho xy equal to minus 1, similarly we can show that y will be equal to minus sigma y by sigma x times x plus sigma y by sigma x times mu x plus mu y with probability 1. So that means we can see that Here y equal to ax plus b with probability 1, but here a equal to minus sigma y by sigma x, which is negative. So when correlation coefficient is minus 1, y is perfectly linearly related with x in negative direction. Okay. The correlation coefficient is a measure of degree of linear relationship between x and y. Okay. The value of rho xy near 1 or minus 1 indicates high degree of linear relationship between x and y, whereas the value near 0 indicates lack of such a linear relation. Okay. Fine. So the positive correlation value indicates y tend to increase when x does, whereas negative value indicates y tend to decrease when x increase. Okay. If rho xy equal to 0, then x and y are said to be uncorrelated. Uncorrelated means there is no linear relationship between x and y. Okay. Fine. If x and y are independent, then they are uncorrelated, but converse may not be true. First of all, when x and y are independent, we know that covariance of xy 0. That implies correlation coefficient will be 0, because correlation coefficient is what? Covariance of xy by sigma x sigma y. The numerator is 0, the whole thing will be 0. So independent random variables are uncorrelated, but converse may not be true. Here is the example, the same example that I gave earlier. If x is a standard normal variable, y equal to x square, then correlation coefficient of xy going to be 0. The reason is we already know covariance of xy 0. We already worked out this thing. So we realize that covariance of xy 0. Covariance of xy 0 implies correlation coefficient 0. That implies x and y are uncorrelated, but they are dependent. But x and y are dependent. Okay. Here uncorrelated means there is no linear relationship between x and y. That doesn't mean that there is no relation. Okay. Here there is no linear relationship between x and y, but we do have a non-linear relationship between x and y. As you know, y equal to x square. Okay. Fine. Problem. Let xy be a continuous bivariate random variable with joint PDF f of xy equal to x plus y for 0 less than x less than 1 and 0 less than y less than 1, 0 otherwise. Find the correlation coefficient between x and y. Okay, what is the correlation coefficient between x and y? We defined as covariance of xy by standard deviation of x times standard deviation of y. And how to compute covariance of xy? We have a formula, that is expectation xy minus expectation x times expectation y. Okay, so to compute correlation coefficient between x and y, we need expectation xy, which can be computed using giant PDF, and we need expectation of x, expectation of y, and standard deviation of x and standard deviation of y. These things can be computed using marginal PDFs of x and y. Okay, first let us get hold of marginal PDFs. Okay, first PDF of x can be computed integrating giant PDF with respect to y. Here y limit is going to be 0 to 1 in the support, so we have to integrate giant PDF, which is x plus y with respect to y from 0 to 1. So integral of x plus y with respect to y is going to be xy plus y square by 2. So after applying the limits, you will end up with x plus 1 by 2. So PDF of x going to be x plus 1 by 2 for 0 less than x less than 1, 0 otherwise. Here the support of x going to be interval 0, 1. Here in the giant PDF, there is a symmetry in x and y. So we can say that immediately the PDF of y also going to be this. Y plus 1 by 2 for 0 less than y less than 1, 0 otherwise. That means x and y having same probability distribution. Okay. At this point, you try to verify if joint PDF equal to product of marginal PDFs. That is, just try to check if this is true. If you see that joint PDF equal to product of marginal PDFs, that means X and Y are independent. In that case, you can conclude the problem saying that correlation coefficient is 0. You don't have to do anything else. But that is not the case in this problem. Here, joint PDF is not product of marginal PDF. That means X and Y are not independent here. So here, correlation coefficient is not going to be 0. We have to find out. Okay, fine. Now, let's find out expectation xy. Expectation xy going to be this double integral. Okay, so we have to perform this double integral with the integrand being xy times x plus y, because this joint PDF is x plus y, and over support x limit is going to be 0 to 1, y limits are also going to be 0 to 1. So if you perform this integral, first of all you write this one as sum of the two integrals x square y dx dy 0 to 1 xy square dx dy. Okay, first we are integrating, let us say, with respect to x. So y x cube by 3 limits 0 to 1 dy 0 to 1 x square by 2 0 to 1 dy. Then this value going to be 1 by 3. Let me write out 0 to 1 y dy, and x square by 2 after applying limits it's going to be 1 by 2. Let me write out 0 to 1 y square dy. So 1 by 3 y square by 2 0 to 1 1 by 2 y cube by 3 0 to 1. So it's going to be 1 by 6 plus 1 by 6. It's going to be 1 by 3. Okay, that's why expectation of xy is going to be 1 by 3. Next, let us find expectation of x. Expectation of x is going to be this integral. Here PDF of x is what? X plus 1 by 2. So we have to integrate this integrand x times x plus 1 by 2 over interval 0 to 1, because support of x is 0 to 1. So if you perform this integral, you will get 7 by 12. Easy, you can verify. So expectation of x going to be 7 by 12, and expectation of y also going to be same 7 by 12, because x and y having same probability distribution because of symmetry. Okay, now let us compute expectation x square, which is going to be this integral. That means we have to integrate this integrand x square times x plus 1 by 2 with respect to x from 0 to 1. So you'll end up with 5 by 12. Similarly, expectation of y square also going to be 5 by 12, because x and y having same probability distribution, right? Fine. Now let us find out variance of x and variance of y. The variance of x, sigma x square, going to be expectation x square minus expectation x whole square, that is 5 by 12, which is expectation x square, minus expectation x whole square, that is 7 by 12 square. So 5 by 12 minus 7 by 12 whole square gets simplified to 11 by 144. So variance of x is 11 by 144. Variance of y also will be same, 11 by 144. So standard deviation of x, standard deviation of y, both are equal to root 11 by 12. Now we are in a position to find covariance of xy. So covariance of xy is going to be expectation xy minus expectation x times expectation y. So expectation xy we got 1 by 3. Okay, so 1 by 3 minus expectation x times expectation y, which is 7 by 12 times 7 by 12. So this whole thing gets simplified to minus 1 by 144. The covariance of xy we got minus 1 by 144. Fine. Now let's find out correlation coefficient. correlation coefficient is what? Covariance of xy by sigma x sigma y. So minus 1 by 144 by root 11 by 12 times root 11 by 12. This gets simplified to minus 1 by 11. Okay. So correlation coefficient between x and y is minus 1 by 11, which is negative and close to 0. So we can say that there is a weak linear relationship between x and y in negative direction. Okay. Fine. Next problem. Let xy be a continuous bivariate random variable with a giant PDF f of xy equal to 2 for 0 less than y less than x less than 1, 0 otherwise. Find the variance of 3x minus 2y. How do you find variance of say ax plus by? We have a formula for that. That's going to be a square variance of x plus b square variance of y plus 2ab times covariance of xy. Okay. So variance of 3x minus 2y is going to be 3 square variance of x plus minus 2 whole square variance of y plus 2 times 3 times minus 2 covariance of xy. So this is going to be 9 times variance of x plus 4 times variance of y minus 12 times covariance of xy. Okay. Again, how do you find covariance of xy? Which is expectation xy minus expectation x times expectation y. So to find out variance of 3x minus 2y, we need expectation xy, which can be computed using giant PDF. We need expectation x, expectation y, variance of x, variance of y. These things can be computed from marginal PDFs of x and y. Okay. First, let us find out marginal PDFs of x and y. Okay. Here is the support of xy. Okay. So this green shaded portion is support of xy. Now let us find out PDF of x. We can integrate giant PDF with respect to y. So here we are integrating giant PDF 2. And what are the y limits here in this support? The y limit is going to be y equal to 0 to y equal to x. Okay. So y limit is going to be 0 to x. So we are integrating 2 with respect to y from 0 to x. So we end up with 2x. So therefore the PDF of x is going to be 2x for 0 less than x less than 1, 0 otherwise. So your support of x is going to be interval 0, 1. Fine. Next. Now let's find out PDF of y. To get the PDF of y, we need to integrate giant PDF with respect to x. Here x limit is going to be x equal to y to x equal to 1. Okay, so x limit is going to be y to 1. So we have to integrate the giant PDF 2 with respect to x from y to 1. So you end up with 2 times 1 minus y. So the PDF of y is going to be 2 times 1 minus y for 0 less than y less than 1, 0 otherwise. Again here support of y also interval 0, 1. Fine. Now let's find out expectation of xy first. Here expectation of xy, we have to perform this double integral. Here giant PDF is 2, okay, and the support is this green shaded portion. So here first y limit is going to be y equal to 0 to y equal to x, and x limit is going to be x equal to 0 to x equal to 1. Okay, these are the limits. So okay, let's do this integration. First we are integrating with respect to y. So if you do that, then y integration going to be y square by 2 after applying the limits 0 to x. So you will end up with x square by 2. Okay, so then you will have the 2 to cancel, then you will have 0 to 1 x cube dx. It's going to be x to the power of 4 by 4, 0 to 1, it's going to be 1 by 4. So therefore expectation of xy will be 1 by 4. Okay, now let's compute expectation of x, expectation of y, and variance of x and variance of y. Expectation of x using marginal PDF of x, that we got 2x, right? So and support of x is 0 to 1, so we are integrating. So this is like a x times f of x. Okay, here support of x is interval 0 to 1, so we are integrating x times 2x from 0 to 1 with respect to x. So it's going to be 2 times x cubed by 3, 0 to 1, so it's going to be 2 by 3. Okay, similarly let's find out expectation x square. So if you perform this integral, you will end up with 1 by 2. Now expectation y, so this is the PDF of y. Okay, so if you perform this integral, easy, equal to 2 times y square by 2 minus y cube by 3, 0 to 1. So it's going to be 2 times 1 by 2 minus 1 by 3 minus 0. So it's going to be 2 times 1 by 6, that will be 1 by 3. Okay. Similarly, you can compute expectation of y square. If you perform this integration, you will end up with 1 by 6. Feel free to verify. Now, variance of x going to be what? Expectation of x square minus expectation of x whole square, that is 1 by 2, that we got expectation of x square minus expectation x whole square. So 1 by 2 minus 2 by 3 whole square, this is 1 by 18. And variance of y, expectation of y square, that we got 1 by 6 minus expectation of y whole square, it is 1 by 3 whole square. Again this also 1 by 18. Okay, I think now we have everything. Now we are in a position to find variance of 3x minus 2y. First let us compute covariance of xy, that is expectation of xy minus expectation of x times expectation of y. Expectation of xy we got 1 by 4, and expectation of x we got 2 by 3, expectation of y we got 1 by 3. This gets simplified to 1 by 36. The covariance of xy is 1 by 36. Now let us compute variance of 3x minus 2y. What is the variance of 3x minus 2y that we got? We got 9 times variance of x plus 4 times variance of y minus 12 times covariance of xy. Now we have everything. We have variance of x, we have variance of y, we have a covariance of xy. So variance of 3x minus 2y is going to be 9 times 1 by 18 plus 4 times 1 by 18 minus 12 times 1 by 36. This whole thing gets simplified to 7 by 18. So this is the variance of 3x minus 2y. Okay, fine. Okay, let me stop now. Thank you.